This podcast features a conversation with Michl Binderbauer, the CEO of Tri-Alpha Energy TAE Technologies, the largest private company dedicated to developing nuclear fusion power, with over $1.2 billion raised for fusion research. The topics that we explore are wide-ranging, delving into the dynamics of nuclear energy and its wider societal impacts.
We discuss how nuclear power serves as humanity's get-out-of-jail-free card, a future civilization where the shackles of scarcity are broken, and humanity enters an age of abundance. Since this conversation, I've experienced nothing but awe, humility, a true sense of gratitude, a surge in curiosity to understand our place in the cosmos. For more information about Michl and TAE, please check the links in the description. And without further ado, welcome to the future with Michl Binderbauer. All right. Hello, everyone. Welcome back to the IBR podcast. I'm so excited to be joined by my co-host Max today and a very special guest, Dr. Michl Binderbauer. Michl is the co-founder, CEO, and architect of Tri-Alpha Energy, or TAE Technologies, and is the co-inventor of many of the company's technological advancements. He's an expert in reactor kinetics, equilibrium, and stability of advanced beam-driven field reverse configurations and aneutronic fusion systems, which both Max and I are not experts in. Dr. Binderbauer holds more than 40 issued and pending U.S. patents and numerous international technology patents, and has authored or co-authored many peer-reviewed publications in the areas of plasma physics and fusion. Michl holds a PhD in physics from the University of California, Irvine. Michl, welcome on the show.
Well, thank you very much. That's quite a nice introduction. Appreciate it very much and enjoying being here.
Michl, in the research for this podcast, both myself and Max found that there's so many different angles that we could approach this conversation, but maybe a metaphor for how I viewed nuclear fusion was a sort of magical way, sort of stars on the earth. It's this idea that we can harness such vast amounts of power that humans have not been able to for so long and could potentially be the next step in human advancement that itself is not fully understood. I want to get your perspective on nuclear fusion. So why don't we start with an overview of what it is and how it could potentially affect all that we do and all that we understand.
Yeah, guys, I think you said it quite well. You know, when I started working on this as a young, naive student, it was exactly that. It was the pull to the fact that humanity is an inflection point in many ways, right? And back then, you know, this is now in the late 80s, early 90s, we weren't at the juncture where we had an understanding of some of the impacts on the planet and the ecosystem that we're causing by our own presence. And, you know, whether it's combustion of hydrocarbons or other things, we leave a big footprint, right? And there are changes that come with that. And that was pretty clear to me. And now, of course, since then, this has gotten, unfortunately, also more politicized, but there's a lot more data available. And we know a variety of impacts that happen, right? And so I think that if you look at that, and you look at that also from the perspective of what we know population growth will do and the advance of use of electric power across the globe, which in the Western world, we're used to incredible consumption levels. It was a great it was a documentary on the BBC. It was about 15 years ago now, I would think, but it's still fully relevant. It was How to Make a Star on Earth. It was done by a British physicist who I respect very much. And in it, they were interviewing a person who was running a wind company at that time, somewhere up in the Bay Area. And he is one of those guys very aware of the environment. He's saying, like, well, I need to reduce my footprint as much as I can. And so he was sketching out in terms of how many kilowatts he was consuming on average and how many kilowatt hours in a day, you know, as a relatively aware person and trying to be conservative, right? And he said at the end, he added up and he said, look, I'm just a hypocritical planet fucker, basically. It was kind of a fun, raw comment, but it in a way characterizes this problem, right? And if you think about bringing the less developed world up to even a fraction of the standard of where we are, it's going to be an incredible impact. And how to do that isn't even something we can fully fathom how to do. Just to put the numbers to it, today we're about 5 terawatts or so of consumption, right? And you're looking at doubling that roughly by about the 2050s. And that's, if you think today, the full available production capacity or generation capacity in the world, it's basically aggregated over what, 150 years or so since the Industrial Revolution. And so it's a massive amount of time. Now we're going to press that in a decade or two. It's incredible, right? I mean, just the sheer mobilization on infrastructure, industrial might, supply chain, capital, all of it. And we know we can't quite do that, and certainly not in a clean way. So this is where fusion comes in for me, right? It's basically they said it in that podcast really well, and I like that term. It's the get out of jail card free for humanity. We can do it, right? And to your point, yes, it's doing what nature does. I mean, nature has been running the universe for, we don't know exactly how many billions of years, right? We know our solar system is on the order of 4 billion years, the sun, and our planet's probably a bit lesser on that order. So you're looking at vast stretches of time, and it permeates. The energy from fusion permeates the universe. It brings the life to us. It makes the materials we're made up of, right? We know those things today. Those are fact. So if you take a hint from nature, this is clearly the way to do it. They're not big combustion ovens in the sky. They're not fission reactors, mind you. They're fusion power plants, basically. Each one of the bright lights we see at night. And so as a kid thinking about these things, it get incredibly inspired and say, this is the kind of thing that we need to solve somehow. And as you also, of course, know, is the science fiction books have been dreaming about that for as long as science fiction is being written. There's the fusion age, right? And I think the cool thing for our generation now, or those of us living today, is that we're probably witness to that singular inflection point, right? And I hope TAE can be a component to that. But I would say what's so exciting today is that now there's this confluence, right, of science and engineering knowledge and technical mastery against this vast challenge. And I think we're at that moment where those things are at the right level to each other, that they can actually succeed, or that we can succeed. And so if you think what fusion then does, well, first of all, it replicates what the stars do, right? It slams the smallest of atoms together and creates bigger atoms. And by Einstein's famous formula, it releases a lot of energy in the process. It's more energy dense than anything else humanity has mastered so far, about an order of 4 to 10 times more dense than fission. That's about 1 million times more dense than combusting hydrocarbons like gasoline in your car or heating oil or whatnot. And so it's incredibly energy dense. You don't need to convert a lot of mass basically to get a lot of power, right? So it should have a very minimal impact in any form you practice it. It can be made incredibly safe. Everybody that hears nuclear gets really nervous and says, my God, are they going to burn down the planet and turn it into a sun? No, of course we're not. That would be far from, it's totally impossible. It can't melt down. It cannot run away. It's not like fission, which is a chain-driven process. I always think of that, and I know my nuclear fission colleagues hate when I say that, but it's fair and it's honest. It's a little bit of pact with the devil, right? Sometimes you start a fission process, and if you have critical mass, which is what you need, it self-propagates, and it's hard to turn off. So kind of once you sign up, you're on for the ride. Now we have, of course, great technology today, and I'm not sitting here saying that fission can't be made incredibly safe. I'm a huge proponent of nuclear power in all forms, to be clear. But if I contrast it, fusion gives you that extra edge, right? Because it's a driven process. So you have to constantly bring the right conditions to bear. You have to keep it hot. You have to keep it the right kind of pressure, and you have to keep it in that happy state. And if anything fails you, it just shuts down. In fact, it's on the order of thousands of a second or so. Everything is over. You can't even have a digital control system fast enough, as nature will shut you off. So, it's an incredible internal safety valve that comes with it. So fusion, in a way, what I describe here sounds too good to be true, right? It's kind of like the nirvana of energy, but that's what it is. And as we're going to explore here now, the implications are enormous. I mean, you can power the demands of the world, not next year, not the next 10 years, perhaps, because it's going to take a while to build. We can explore that a little bit further. But over time, it will become, and I would say, if you go asymptotically towards the end of the century, it'll probably be the most contributing generation technology in our utility grids, and it will do that with limited impact on resources or none, depending on what kind of fusion ultimately we can commercialize in the end. And so you're looking at something that has very low resource intensity, has essentially infinite fuel. If you look at what you're burning basically, or building from the small elements to larger elements, you're taking hydrogenic species or light elements, like we're interested in boron, It's element 5 in the periodic table, right? These are in vast abundance in the oceans, on the crust. We know there's about 100,000 years of boron available to humanity terrestrially if we were to fuse that with hydrogen. And that's based on consumptions around 2050, where I think we've sort of max population and hopefully have a good quality of life across the planet. So it's a good indicator of sort of average use thereafter. And 100,000 years. I mean, how long has humanity been around as a culture? What, the pyramids are like 5,000 years or something, right? I mean, you're looking 100,000 years is an incredible time span. And so you truly get out of jail free for this, right? It is the end all of that. And when you look at what that translates to, and this is the other thing I've thought about more recently as I got older and thought about everything else that impacts human life, health, access to, of course, the basic necessities, food, water, healthcare, and so on. It all goes through the nexus of energy, right? Without energy, you can't do any of this stuff. And so it's a huge equalizer in impact force. It drives our cost. It drives the economics of almost anything we consume, use, or have around us, right? And so if you think about it from a perspective of energy now becoming abundant, you're literally translating humanity's entire perspective into an age of abundance. And I might add, that's actually, in a way, a scary thought too, because our entire cultural and economic, arrangements today as a species are driven by constraints. We've adapted to those, right? In fact, the scarcity of a lot of things drives value assessment. Gold is valuable and other things because they're scarce, right? And if they weren't scarce, they wouldn't be valuable. And so our entire societal value set, in a way, is, I'm afraid, built on the constraints coming from scarcity. So you take that away, and you now, at a so such fundamental level as energy, and make it abundant. What actually happens, right? And it's a great problem to have, and one I'm sure we will eventually get to make benefits from and draw use out of. But there's a transition. A world of abundance isn't just trivial. It's wonderful to have, but it's going to take us a while to grow into. So fusion, to me, sort of a lengthy sort of expose on it, but it's all of that, right? And we can hook into here now wherever you guys want to go. But that's what I see, and that's what it means to me. And this is why I'm working on it, and why a company like TAE finds, hundreds of people willing to donate their lives to that, and whatever else you need in resources, investors, and other things.
It is really a profoundly exciting notion, the idea of fusion. It's a tremendous problem. Constantly, we're reminded of overconsumption, of the climate crisis, of our inability, of the unsustainable use of resources that we're currently undergoing. And fusion really represents a solution to that, a possible solution. But just something that you touched on that I think it'd be useful to delve into a little bit further before we talk about societal impacts or engineering or how to make it happen, which is just the comparison between fusion and fission. Because fission is the type of nuclear energy that I'm sure most of our viewers are more aware of. We have a fission power plant in Ontario, just close to Toronto and Pickering. That type of energy is far more developed and far more disseminated than fusion, which is still in the process of development. What are some fundamental differences between the process of fission and fusion? And why are we so far ahead with fission in comparison to fusion? What are some of the impediments to the development of this new technology, and this new incredibly exciting technology, I might add?
Yeah, this is a great question, and we can spend an hour on that in many facets, but I'll try to summarize it quickly. So fission, of course, fission and fusion are both, in a way, nuclear. They're sort of cousins or siblings in the nuclear taxonomy, right? And they both essentially convert mass in an atom through a transformation process into some amount of energy that gets released. And this is really described by Einstein's famous E equals mc squared, both cases, right? And so, so when you fundamentally, when you look at the periodic table, if you take super heavy elements like uranium, plutonium, and those kinds of transuranics, even, then they're typically unstable in nature, right? They're so big that they have this propensity to fragment a little bit. And by the way, the most stable and bottom of this well, if you will, is somewhere around iron. Okay, so iron tends to be the kind of bottom of it. And you can reach that bottom from either the light elements have a propensity to, that you can bring them together. The heavy elements have a have an opportunity to be broken apart. And then you get sort of the bottom somewhere, right? And we call this in the physics world the nuclear binding potential. There's a potential energy that's stored in these nuclei, and it's kind of like a U-shaped function. And so you can come down one wing or the other wing. Now, it turns out that the heavy element wing coming down is a sort of shallow decay to the bottom. And on the fusion end, it's a very steep one. And so what happened is in the early going, people understood that both of those are potentially possible. This is like earlier part of the past century, right? Advent of quantum mechanics, a lot of nuclear physics was discovered and understood at that time. So they knew that both of those things are possible. Now you're asking how to first differentiate, and then why one is further along than the other. So what happens in fission is, right, as I said already, you're breaking stuff apart. And that actually happens naturally. I mean, there's only a certain abundance of somewhat stable heavy elements. Many of those have eventually a decay process, but that can be thousands of years. And so, statistically speaking, there's some material around. It's not nothing. It takes a long time for it all to sort of decay away, but they break apart. And it turns out that what then happens when that breaks apart, it typically releases what we call neutrons. And these are parts of the atomic cores. For those that took science classes and remember that, right? The atomic core is protons and neutrons. And then think of that like the core of a little mini solar system. And then around it, you've got this cloud of electrons, the little planetesimals. And those are the negative particles. And in the core, you have the protons positive, and you have these neutrons that are neutral. They have no charge. In the nuclear fission process, for instance, the neutron usually on a decay gets released. And that neutron then can trigger a neighboring atom that's also in this sort of metastable state, heavy nucleus. If that neutron hits it in the right way, it can actually induce a decay in that atom. And so if you bring enough of them together, then just by the nature of the process, somewhere one will start. That releases a neutron, and if that neutron gets captured somewhere nearby by another heavy element, then that has a high chance to decay. And if it's not that one, then it'll be the next neighbor. As long as you pack them closer together, you eventually get to what they call critical mass, which means there's now enough probability in the system that it can trigger continuous decays. And so that's a question of not much more than understanding how much material do I need probabilistically to get that to happen. And that's what, for instance, Fermi did in Chicago, right? Famously at the University of Chicago first. And then very quickly that translated to, okay, if we make cores of a power plant with enough nuclear material of the right kind, and we understand the decay process, we can pack enough to get this to work. And then what happens is every time one of these larger atoms decays, not only does it release more neutrons that can trigger another decay, that's the chain effect, right? But you can also, every time you get by Einstein's formula, a reduction in mass. So when you measure the mass of the fat guy first, and then the mass of, say, the daughter particles that come out, the total mass of those daughter particles is a tiny bit less than the mass of the fat guy you started with. And that gets converted by Einstein's famous formula to energy. And of course, c, the speed of light, is a gigantic number. You square it, it's an even bigger number. So you multiply a tiny amount of mass by this massive number, you get an enormous amount of energy actually per decay process. And so that's what strings together. Now, as you can appreciate, the problem with that is that thing can run away from you, because once it's naturally going, it's kind of hard to stop. And so people have devised controls to kind of to break the chain, if you will. If it gets too far ahead and it starts to overheat, too much energy gets produced, right? And that's a very well controlled process today that we deploy in power plants. But occasionally something can go wrong, right? And when it goes wrong, I'm afraid then you get from freak accidents to really serious stuff, the kinds of things you read in the paper, right? And that's
like Chernobyl, for instance.
Yeah, Chernobyl or Fukushima, or 3 Mile Island, and those kinds of things. And of course, that is a part of the process. Now, as I said earlier, we have gotten smarter in the engineering world on designing things that are now inherently safe. And even with operator error considered, you can make them, nothing humans do is 100%, but it's really high safety factor. And those are the latest generations of plants. And I would perfectly live next to one of those, and it wouldn't worry me, because I know the chance that can go wrong. There's a much higher chance you have a car accident, you stumble over your own feet and crack your head, God forbid. I mean, then that going wrong, right? or having an accident anywhere else in your life. So I think it's in that sense perfectly fine. But it basically, again, notionally, technically, take heavy stuff, break them apart. So now on fusion, on the other hand, you take the light things. And I said this gets you down to the bottom of the nuclear binding potential too. That is steeper. So per reaction, therefore, you get more energy out. So the difference in mass in one generation to the next, here you start out with 2 particles and you add the mass of those, and it's bigger than the slightly fatter guy you're making. And that difference in mass gets converted. And so in that case, it turns out per reaction, you release typically, somewhere between 3, 4 to 10 times more energy than a breakup. So it's steeper slope. One is shallower and the other one is steeper. And they get to the bottom there. And so the stars do that. They basically build with hydrogen to helium to lithium, beryllium and onwards, and they build the entire periodic table. And while they built to the fusion process, builds it out to the bottom of the well, that's iron, and then there are other astrophysical effects in the end of life of stars that produce the heavier stuff, of which there's obviously less. Anyhow, but the universe is permeated by the light stuff, right? And it's where you start building from. Those are our essential building blocks. And so fusion is the opposite. Now, what you see here is there's nothing self-propagating. Once you get one event, you have to pray to find another way to bang 2 particles perfectly together to get another interaction. So fusion is also probabilistic in that sense, in that you just have to have a lot of collisions, and occasionally you get one that's really perfect. And what you can appreciate too is in fusion, you actually operate under what's called a plasma state. So what happens is you need violent collisions. Why? Because these atomic cores are positively charged. I said earlier, there's protons and neutrons. The neutrons are neutral, but the protons are positively charged. When you take the electron cloud away, which makes the overall atom neutral, there's many electrons that are negative as there are protons that are positive. If I take all the negative particles away, I'm left with a residual positive core. And that core, now being put next to another positive core, repels. You may remember, like particles, like charges repel, opposite charged particles attract, right? So here's the problem for fusion. Nature doesn't want to come together. And in classical physics, there is no solution to that. In fact, the closer you bring them, the more infinite the force becomes that pushes them apart. Okay, and so it turns out quantum mechanics has an elegant solution to that. They call that tunneling. It's like you've got this infinite mountain, but if you bring them close enough, you can dig a small tunnel through that and they can merge up, and fusion takes advantage of that process. And then you get a reactive event. So you have to bring them close together. And so as you're working against that repulsion as these particles near to get them to that critical sort of distance, you need a lot of energy in that approach. And that means you need somewhere a lot of energy in the material that's buzzing around in these particles. And that means in the end heat, and you make it hot. Temperature is a measure of random energy in a gas, right? And so what happens now we get with a plasma is, if you want to make fusion, you start with something cold, room temperature, a gas, a liquid, could be a solid, and you add energy to it, and then it starts to transition, right? We all learned this in elementary school when they first talk about solids, liquids, and gases. Well, what they don't tell you is a plasma is the final state. When you add more energy to a gas, it ultimately becomes a plasma, and a plasma is basically the point where these electrons are stripped off from the ions, and then you have a cloud of positive charges and negative charges swirling around, but they're not bound together in an orderly way. So it's beyond the gas, and that's a plasma. So plasma is like a charged gas.
Okay? And where might people find an example of plasma in everyday life?
Yeah, so that's, of course, why they don't teach it to you, because it's not very common.
Yeah.
In fact, it's transitory for most people. In the old days with neon tubes that, the youngest kids don't remember because they haven't lived with them. It's all LEDs these days. Those are based on cold plasmas typically, and that's an example. It's as closest to our living room that you can find. In nature, you'd find it in lightning strikes. So when you have a lightning discharge and we all see the bright arc, right? What actually happens is the gas, the atmospheric gas, the air gets ionized. That's ionized means it's electrically you'd strip electrons off, these atomic neutral atoms. And now you actually, as it recombines, as these electrons join back in, that releases all sorts of radiation, but certainly optical. And we see this with our eyes. This is the lightning bolt, right? So during that moment of discharge, this column of air has turned into a local plasma. So that's about as close as we get to it. And it's interesting that, in fact, 95% of the universe is in a plasma state. It's just our neck of the woods that doesn't have that, right? So it's kind of peculiar. And that's why usually in science class, they don't overload you. It's already hard enough to talk about 3 states of matter, but the most pervasive state of matter is plasma. So now you've got a plasma. Now it's hot. Now you can talk about fusion. So now you are essentially finding that on occasion, as these particles randomly zip around in your bucket that's super hot, where you have your plasma, there's one collision out of many, many, many that it's just perfect. These particles come head on and they get close enough.
Right? How many collisions are we talking about?
Well, that depends on a lot of conditions, but it's like a needle in a haystack. I mean, you could have 100 million collisions and you get one.
Wow.
Okay, so it's very rare. It's a very low game of probability, to be clear. Now, you can make. There's a lot of things you can do to try to enhance that. Like, for instance, you can picture you heat them up more, you pack the particles closer, or you can do a few other little tricks that enhance that a little bit. But the fundamental problem is it's a rare event, and that's why you need lots of collisions. And statistically speaking, we can't control what each particle does, right? So you have to heat up this appreciable volume. And by the way, when we're talking temperature, to get that out of the way, we're talking crazy temperatures compared to what we experience globally living on the Earth, right? We're talking 100 million degrees inside of a fusion reactor. Okay, now put that in contrast. The sun, actually, the core of the sun is about 10, 15 million degrees. Okay, so you're looking at an environment that in the fusion plasma terrestrially is hotter by a factor of 6, 7 or so what we practice today than the core of the sun. So it's quite remarkable, actually. But you also have to appreciate that the amount of particles, not the sun actually does what the sun does is really wonderful because of its massive gravity. It can attract these particles, compress them in the core because of the pressure it can generate from the gravitational force. So it can pack them really densely, and that helps. So that's why the sun can actually produce power at lower temperature, because it makes it up with what we call density, right? So it's more compressed stuff. Terrestrially, we use electromagnets, or you may have read about people trying to do this with lasers, compressing this gas and heating it. And those things are kind of a bit weak compared to the massive gravity of the material that's comprised in a star, right? So we have to be a little bit more limpy, and we have to make up for the lack in packing with higher temperature. And so this is why you need to get to 100 million degrees minimum. But if you do, you now have a situation where on average, you will find sufficiently enough particles that per every unit of time will bang together just right and cause a fusion event. And then, as you keep doing this, you get eventually sufficiently energy produced in that process. But here's the benefit, right? This is hard, obviously, and we'll talk about how hard that is. That's why it's taken so long. But it's also completely safe, because if anything goes wrong and that thing cools off and is no longer capable to react, it stops. And that's why these things shut down by themselves. So one hand on fission, it's hard to stop. Here, it's hard to start and even harder to keep going, right? Yeah. So if you ask me now, why is one ahead of the other? I hope it's already starting to be a bit evident. In that one case, once they understood they could pack stuff together and they get fission to occur and self-propagate, that was possible with less engineering sophistication and technological advances were needed to do it. In the case of fusion, you now have a lot of challenges. First of all, you have to figure out a way, how do I get this stuff to 100 million degrees? And more importantly, how do I keep it there? And now you may ask, of course, 100 million degrees, Michael, why don't we burn the Earth up and turn everything into a meltdown, right? Well, the answer is that the amount of particles we actually heat terrestrially inside of one of these fusion cores is really small. In fact, it's, like 1 million, 10 million times, it depends on conditions, less than the air in the room we breathe. So it's very rare. So you can almost say you're making energy out of vacuum. So you have very few particles inside this vacuum system, and now you make these super hot. But the total energy that's stored then in this cloud is not much. And in fact, when we think of temperature, we think of a hot stove plate, right? And you touch that and you know what happens to your hand. You're in the hospital.
Ouch.
Yeah, severely ouch. If you were to, and of course you can't do that, but if I could stick my hand into a fusion reactor core at 100 million degrees, the hand would cool that plasma off, but
Really?
I
Wow.
wouldn't fry my hand. In
Yeah.
fact, today, we run our plasmas is about 70 million degrees in the experiments that we do. And that's enough. That's like think a cubic meter of this plasma at these temperatures. If I were to put an ice cube, the average ice cube in our fridge or, soft drinks, you take one of those, you put it in, it would melt that ice cube, but it wouldn't even heat that puddle of water up. It'd be enough energy to turn the solid ice into its liquid state, into water. That's it. So you see, it's an extremely ethereal deal. And so the problem is when that hot cloud makes contact with the wall, in our experiment, for instance, now it's not going to melt the wall. It won't even measure appreciably a change in temperature of the wall, because the wall has so much capacity to absorb energy relative to how little is in there that it doesn't change the state of the wall. On a reactor, it's different once you make power, because then you are constantly generating fusion-based heat, right? And that heats up the wall, and that ultimately then you need to remove, and that's where your energy flow comes from that you want to send eventually to the grid. And we'll talk about that in a moment. But these experimental machines right now, we can make 100 million degrees, and you can stand next to it, put my hand on the steel, there's nothing. And in fact, what happens is it constantly evaporates on you. It literally cools off faster than you can keep it hot, right? That's the hard part. That's why fusion doesn't exist today. And you need a lot of scientific understanding. How can I manipulate this ethereal ball of stuff? And by the way, right, you can't touch it with stuff, because once I do,
Yeah.
I cool it off. So I have to do everything remotely. It has to be held inside this cocoon of other stuff in this vacuum system, and with the magnets and whatever other ways you use to heat it or manipulate it. And you have to keep it off the wall so it stays happy and hot. And that is really difficult to do. And it's, in fact, probably the greatest engineering challenge that mankind so far has faced. And that's why we don't have it. But we are, as I said at the beginning, we're getting very close. So sorry, this is a long answer, but I hope it elucidates.
No, it's
No,
absolutely interesting.
golden.
Yeah, I guess on that note, you said nuclear fusion. To summarize, it's so delicate. It's so delicate, and I guess that's one of the largest differentiating factors between that and fusion. That and fission is that it's almost as a needy child, right? It demands a lot from you as an engineer to put into it. Do you look at the stars sometimes and are in awe of how they sort of do that? As an engineer, I would assume you're putting in so much effort, and stars are doing it almost subconsciously, right? At a lower temperature, that is too.
Yeah, 100%. Look, I mean, I actually was, before I decided to end up doing what I'm doing, as a young kid, it was astrophysics all the way. And it's funny, I have a son, he's a teenage son, who is thinking of astrophysics, and I didn't push him there or anything. But obviously, if you're a curious kid and you love science and you look up, I mean, what more inspirational thing can there be, right, than looking at the night sky and saying, what's out there? And once you learn in school, or your parents teach you, that these things are stars and they're made up of these balls of material that then fuses and creates energy and light, and we can see them therefore, and they form stuff, you think, my God, it's amazing, right? I mean, it's such a beautiful order how the universe builds us up,
It's absolutely
material
interesting.
to make us, right? Then he gives us the energy to actually exist. It's remarkable. And yeah, I mean, all the time I do. And I also ponder the question, Einstein used to say, God doesn't roll the dice, right? But he made it hard. I mean, but at the same time, I mean, it's possible. And this is the wonderful thing. So when you look at, so fundamentally now you appreciate now what we need to do, right? So now you can translate this in the language of science, physics, and mathematics, and you can say, okay, so what do I need? What do I need to make that happen? I know there's a certain evaporation rate or leak rate of energy and particles that I may not ever be perfect. I can't hold everything in, right? It's like if you start with a box and you put in the center of the box a little bit of gas, over time it'll fill the whole box. It'll be less dense than when you put it in the little dense moment inside, and then it kind of, there's motion indigenous that just distributes it. You can't fight all of that, right? So you're going to have a loss. So the question is, at the best that we think we could do, that loss compared to the capability to make, it turns out there's a positive balance. So it actually, it's a bottleneck you have to get through, but there's a way to make it work. And the wonderful thing is, in a way, and maybe this was given to us by the creator, if you want to go there, or say, the whatever makes the universe. I'm not the most religious person, to be clear, but you somewhere get a little bit, not dogmatically religious, but maybe spiritual is probably a better way to say, right? There's something there, and there's an amazing order. And I've met some of the brilliant minds of our time, Nobel Prize winners and others, through what I do, and they get interested, and I reach out, they reach out, and we talk about these things. And one of my good friends for many years has been Arno Penzias, who discovered the microwave background, right? And basically proved kind of experimentally the existence of the Big Bang. And he said many times to me, he's like, once you understand how star formation works, and then the production of material, the construction of the elements, things in stars, you realize, and it's all defined by these what we call physical constants. If you look in the back of a physics books, you will usually find in elementary text, there's like a list of the physical constants, the radius of the Earth, and those things are in there, but also the charge of an electron, and those kinds of things, the mass of an electron, those kinds of, and in the elementary school, in the elementary physics courses, you always have to manipulate stuff where you have to plug those things in, right? These kinds of numbers, gravitational constant, so on. And he said, look, if any one of those quantities, those fundamental quantities, would just be a tiny bit different than the way it is, none of this would be here, right? So it's remarkable. And so in the end of it, yes, I'm deeply inspired by all this, and I wish it would be as seemingly trivial as nature has made it on the big scale. It turns out, it's much harder, but the wonderful thing is it can be done, at least to a degree. And I think that, to me, is the wonderful thing, that again, the universe left us this little opening and said, you earthlings, here's your window. We'll make it tough on you, but it's solvable. I firmly believe it is. And when you look at the fundamental physics that needs to come together, it can be done, and it can be made work. And now I think we are really, really close. This is a standing joke. It's always 30 years away. I definitely do not believe that's going to be the case.
Yeah. Now, let's talk about what the universe has given us. I guess first question, have you watched Oppenheimer? And if you have, what were your thoughts about that movie? Maybe you can go insofar as a movie review with Michl, but also, how do you think of that as maybe lessons that you could approach and
so
apply
interesting
to
enough, so I've not seen
Oppenheimer.
Shame on me. I will tell you, my life right now is so consumed. I used to be an absolute book rat. I was never a big movie buff, but I used to devour books. I get to do so little of that right now that a lot of I have books on the shelf that, when they come out, it's like, I gotta buy this and read it. And I tell myself, after I've put the Amazon order, and I'm like, who are you kidding? You're not gonna read that near term. It's okay, in retirement, I'm gonna read it. Now I have this I call it the retirement bookshelf over here. The walls are bookshelf, and there's the ones behind me that are my bread and butter books that are technical, that I have to interact with on a not daily basis, but sufficiently so. And then there are the ones I want to eventually read. Now, of course, I know Oppenheimer's or the entire gestation of the Manhattan Project and stuff, and so I have a sense for it. I think it is. There are a lot of parallels when you develop stuff that go deep in the unknown. In fact, even more abstractly, I don't even think it has to be in science. It could be essentially in anything. Something like what Elon Musk is doing with rockets, and even Tesla, or you take, anything that's frontier work, right? You're up against enormous obstacles all the time. We luckily, all that of us that entrepreneurially are driven in doing that, we underestimate the complexity. Naivete is an absolute must. I'm 100% convinced on that. It's like I'm a living example of that. When I became, obsessed with fusion, if you will, and after I got my PhD, was thoroughly convinced that we had a way to do that. And of course, I didn't understand how expensive that would be, both in terms of personal energy investment, time, dollars. The technical mountain that has to be scaled, all those kinds of things. And I think that's one of the testaments to one of humanity's great strength, which is there are those of us, clearly, maybe call us stubborn, who are not willing to give up, right? you just steadfastly follow. And I was raised by a serial entrepreneur. My dad built 3 businesses in the medical field, and I saw the ups and the downs occasionally. I mean, not everything is always vanilla. It goes in its cycles. But he did well in the end, 3 times over, and that helped me to sort of say, okay, entrepreneurial stuff isn't that bad. I mean, there's a happy ending at the end. But the reality is, the moments in between are god awful, right? And he always taught me, he said, never surrender is sort of the main motto you have to follow. And I think that's, if I think about the Manhattan Project, I think about any technology development, our quest to go to the moon, any one of those, right? They're driven by people who are not only creative and have vision, they have naivete, just like children. You have to have that optimism, and somewhere you cannot surrender to an obstacle, because if you do, we wouldn't have any of this stuff, right? And I think my journey, if I look back at it now, now all I know, would I do it over again? Yeah, I will say that now because that sounds right. Yes, of course I would. But honestly, I mean, maybe in hindsight, not sure. I love every moment of what I do, and I probably would go back because I wouldn't have the knowledge, right? So I would do it again. But basically, what happens is you leave base camp. You're scaling a mountain. You're totally in the inversion layer of the fog, dense fog around. You have no idea. All you know is there's a path up, and there is a mountain there, and you want to climb it. And now you're climbing out of base camp, and somewhere you get to the inversion layer, and so you're migrating above the cloud. And once you get to that point, you realize, shit, I'm only a quarter up, an eighth.
There's a lot more to go.
But at least you see the summit now. But now the sobering moment happens, and you say, yeah, I got a lot to climb. But that's the other wonderful thing, right? That's where never surrender comes in. Plus, then you do the calculus. You say, man, I've already expanded so much. I'm already here. How could I possibly turn around, right? So you keep going. And I think that's so. Sorry, I can't answer exactly the innards of the Oppenheimer movie, but this is a kind of philosophy that I believe underlies all of these, whether it's great discoveries or turning a known principle into practice and engineering process and products eventually, or ability. It's fundamental to it, in a way.
And I think, of course, sacrificing your reading time or current books, considering the profound civilization-altering effects of nuclear fusion, is definitely a worthwhile sacrifice. But I think something that I use, an analogy that I use to kind of understand the state of nuclear fusion at the moment, is that at the turn of the 20th century, there were a bunch of different companies and government organizations trying to develop an airplane, something that could fly. And while everyone agreed on what an airplane needed to do to fly eventually, no one could really agree on the particular mechanisms or engineering that was required to make that happen. Now, at TAE Technologies, you are using an approach to creating nuclear fusion that is different from most in the industry, or most that was pioneered since the Soviets shared their technology in the 1960s. Could you explain a little bit about what makes TAE Technologies' attempts at nuclear fusion different from others in the industry? Is it more exciting? Is it more dynamic? And ultimately, what was behind the thought process that led you to develop this new type of nuclear fusion?
Yeah, absolutely. And I think that's critical. I mean, I'm a practical person. I mean, I love theoretical physics and math, and I got my PhD doing actually theory, not experiment. But that was just because I thought about it, and I said, on a sheet of paper, life is more controllable. And I have friends at that time who went to graduate school in physics experimentally, who took double the time because something blows up, something out of your control happens. I had a friend who was working on some experiments in particle physics, but they were using one of these NASA weather balloons to send something up to take measurements. They took 2 years building the darn thing. The balloon blew up. It wasn't their fault, right? All the gear gone, all the 2 years of slavery. The professor just said, okay, we got to get a new grant, build a new one. And he's like, well, what happens to my PhD? Well, you're reset, my friend. But the good thing is, well, I'll cover your stipend for another, whatever, 7 years. So I said, okay, no, I'm not going to do that. I'm going to work with pencil and paper. I can control that, right, to a degree. You don't know how, maybe the problem is too complicated and you don't find an answer that they give you a degree for, but it felt like more controllable. So that's what I did. And then you end up, going out into the real world. And what I really wanted to do was do something that's practical. And fusion has that connection. And more importantly, now getting to why TAE and its specifics, we decided that I shouldn't even say the credit goes really to Norman Rostocker. And so Norman is my PhD man, was my PhD mentor. He unfortunately, he is a fellow Canadian. He's a Torontoan. He went to the University of Toronto, studied math there, then ended up at Carnegie Tech, studied physics there, got his PhD, and during his postdoc years did some incredible work in solid state physics that landed his postdoc mentor at Carnegie the Nobel Prize for work that today was called KKR theory, which is a fundamental way to calculate properties of solids. And Norman always, he wasn't upset about it all, but he was just joking and said, man, made a wrong, just should have hung on another year till he would have shared the prize, right? He wasn't about prize. It was sort of a side comment, and I know he didn't really mind it at all. But he was just an incredibly ingenious, intuitive scientist. He ranks in my world, he ranks up there with Einstein and the best. And then maybe obviously I'm a little bit tinted, but he was that kind of incredible, brilliant scientist, but he also was an incredible human being. He had a very intact and functional family, 4 kids, wife, very happy life at home. I know that because they were so generous. They would invite all of us graduate students in for dinner if we didn't have a meal or something. They would allow us to come in. I mean, just wonderful people. And, you learned from him more than just science. It's sort of way of life. And a lot of the really brilliant scientists that I have met actually ended up with awkward family lives or something, because they're so absorbed by the work they do, right? It's not evil or anything, but they can't, coming out of that ivory tower to go down to where mere mortals live in a way is difficult for them, right?
Right.
And the other thing was with Norman that while he could live in that ivory tower, he didn't make you feel deficient. Always felt like a complete imbecile next to him. It's like, I'm clearly a mere model, to make that very clear. I'm not an ivory tower guy, but he was, right. And he was the kind of person who would make you feel at ease and allow you to experience to the level you could, and never make you feel inferior or not part of what's going on. But now when I met him, he had a very good sense for fusion as a whole. He was one of the, I would say, 5 or 6 guys that you could argue, I always call them like the high priests of plasma physics. They kind of developed the whole field. It's not that old, right? There's a branch of physics that exists. Maybe now it's 70 years. I don't know. Somebody may hit me for that and say, no, you're wrong, Michael. It's longer than that. Something like that. It came about definitely during the first half of the past century. And he was one of those early pioneers, and they developed all the theory underneath it. They did some of the fundamental experiments. They started to understand how hard all this is, right? And then they absorbed some of the knowledge, he said, from the Soviets with tokamaks and so on. And so by the time I became his student, late 80s, early 90s, he was just about in his 70s, and he had an illustrious career, of course, won the Maxwell Prize and all the foundational stuff, got accolades and awards for his work, fundamental work. And he was a big insider, but at the same time had this maverick mindset, and as a true scientist, be very factual and not politically driven or money motivated by grant, the way grants flow sometimes. He was very much in the here and there and now, and looked at it and said, if we wanted to make practical fusion, I'm afraid everything that I've encountered so far in my career may not make the cut. It may not be economic enough. It may not be practical enough. You can't build it in a reasonable way. So all this stuff works for the utility sector and so on. And then, of course, the fuel cycle, the idea that you use tritium, you have to interact with the world that's clandestine, that makes, it's in our hydrogen weapons and stuff, in the thermonuclear weapons. So there's handicap around all that, right? And so he said, if there's a true way to do it, it's probably different. Now you may ask, if that's knowledge to him, why isn't everybody else in the same opinion? And well, I think people deep in their hearts would agree with what I just said. However, as scientists, we're also trained to take the smallest next step, right? Small step for steps for small feet. And so what happens is people look for the nearest thing to do. And that happened to be, in that case, tokamaks, because it worked better than anything else people had tried. The tritium fuel was sort of the given for that. And so they kind of live in that thing. And he was willing to look out, get above it, bigger picture, and say, this isn't quite a good fit. So we began working on something different, driven by what he liked to call the end in mind. The end in mind is obvious, right? If I were to ask you, Max or Krish, what would a power plant look like? Well, it should be, if it can be small and doesn't require a lot of resources locally, right? It's very clean. There's no pollution coming out, no radioactivity. The fuel is cheap. I can build them maybe in a factory, so I can learn from economies of scale. I can easily ship them wherever I want with the current logistics system. That'd be pretty simple. I mean, it's not rocket science, okay? So you take those metrics and you say, does, for instance, a tokamak meet those criteria? Well, I'm afraid you get X's pretty much on every one of them, maybe 1 out of 20 that you'd say checkbox. Okay, and so that's kind of what, so we said, so how do you then make that gap? How you bridge it? And so we kind of reverse engineered, and I shouldn't even say we, he did. I was too green behind the ears to do any of this, but I noticed what I liked about him and I liked about the approach was, here's a guy who's incredibly theoretically capable in every sense, top-notch science, but he has a sense for the practical. And so and that's what attracted me, and that's why I worked with him. And we began then building, and that's what led to TAE, a concept that was driven by the end in mind. And so you start to look for the criteria I just mentioned. Now, is everything perfectly matched? No, it's not, because it's impossible, right? But you're striving for an optimal compromise that gets as close to that as you can. And that's what bore out TAE ultimately. And just to give you a flavor for we can spend hours here technically, but
I wish we could.
Yeah, I know, but I mean, on the high level, essentially what it is it's gleaming a few ideas and principles from accelerator physics. And Norman had a good reason to go there, because when I was talking about what he did in solid state, he also worked on accelerators, not just fusion, amongst other things. He was a very polymath in many ways. And in accelerators, and I'm talking now about machines like CERN, like the big guys, like the big machines we've had, Fermilab in the US when it used to run, those kinds of things. In those machines, you basically accelerate charged particles to the speed of light, right, or close to, and then you bombard them at each other in these collision chambers, and then you look at the fragments that come out and you try to understand the makeup of matter. Now, people get a Nobel Prize today, not for the tool, but for what the work they do with the tool, right? So it's a highly evolved field. And in fact, what they do, if you abstract it, they make these very low density plasmas, little blobs of plasma, and then they accelerate that. It's a cloud of charge. Usually it's not one charge only. And they hold those in electromagnetic tunnels. Plasma physics towards fusion is trying to do that. Electromagnetic bottle, put charges in. The difference is the density is much higher in the world of fusion. And obviously, we don't go to the extreme energies. Now, mind you, if you look at CERN, and you can look this up on their website, and you ask, what's the temperature of these clouds when they collide? And again, remember, physicists now mean temperature isn't the hot stove plate. It's the way the random energy in this cloud of material. You will see, they will say it's on the order of 5+ trillion degrees. Trillion degrees. Okay, so we as humanity have found a way to develop reliable, operable tools that can actually create this. And you say, okay, why don't we just take that and then turn that and make it a reactor? Well, the density is too low. So you get too few reactions. I mean, they basically are fusing and splitting particles on every experiment. That's what they do. But it's a handful of particles, and they need the output of a power plant to achieve that. It's totally inefficient. It's not the right realm of engineering embediment of the ideas, but there are physics principles underneath it that obviously are really well understood, and they work. And so the question Norman posed when I started working with him, can we take those functional principles and can we transplant them or fuse them, no pun intended, into fusion, right? And can translate that physics into the reactor space, fusion reactor space, and exploit it. And a lot of people thought that was totally impossible, and that, of course, you change density, you get more collisions between particles, and that leads to the diffusive problems that we find in the reactors. It turns out that's not the case. There's very subtle reasons for why actually accelerator physics can work and can actually give you the same benefits in a fusion reactor than it does in a CERN machine. And we've now reduced this to practice. So when I got my PhD, I worked at all the mathematical theory first, and then we applied it to this idea of this transplant where you create in a higher density environment a kind of physics basis that is akin to the accelerator, less so the sibling fusion reactors of other people's design. And so we began building that theoretically and then with computations. And by the late 90s, we were very convinced that, absent some unknown, which is obviously always possible, that we could probably build something, and then that something could achieve incredibly high temperatures. And we also had theoretically then understood that the physics of the accelerator works better at the higher temperatures actually than at lower temperatures. So it in a way, it bootstraps you to conditions when you go to higher temperature. And in particular, hydrogen and boron, we didn't talk about this earlier, but you need about 1 billion degrees to cook that. And in fact, that was one of the ingredients when we looked at fuel availability and complexity, using something that's non-radioactive, that's in abundance, versus something that's highly radioactive, classified, and no abundance at all. Because of its radioactivity, it decays very quickly. It has a 12-year half-life. So if I put a bunch of tritium in a box, after 12 years, I've got very little to nothing left, right? That's what half-life is. It's not, half of the material is sort of decayed, but it's exponential, so it keeps decaying rather quickly. So in nature, tritium fuel for the conventional fusion doesn't exist. We have to breed it. So if I don't have to breathe, but I can just grab it and it's a light element, I can filter out the water. Or, we here in the California, we have in the Mojave Desert, these deposits that are right on the surface. People mine that by the metric ton. This is an ingredient that's used in detergents, soaps, cleaning products. It's dirt cheap, it's a commodity product. Think of something has zero fuel cost, essentially. Incredible, right?
Wow.
Versus
Yeah.
tritium is I think it's $30,000 a gram. Pretty big difference, right? I can buy a container of boron for a few pennies, basically. I mean, it doesn't even affect the economics of it, right? Now, we also looked, of course, what fuels are available, and it's sad enough that the bookshelf of terrestrial fusion fuels is actually very small. There's only a handful of fuels, and the most extreme in temperature is boron. But now we said, okay, if we can make the accelerator physics work, we can actually operate with boron, potentially, right? We have to, of course, develop all the stuff to make it functional in the lab, but it seems on paper it's possible. So that's where we started, and then we went and tried to get what academics do. You get DOE money or a federal agency money, right, for research. This is typically what happens. And this was a time in the 90s when interest in funding in fusion went really low. It wasn't the 70s with the oil crisis. We were in sort of a plentiful energy environment. And people had other problems that they wanted to deal with. The Clinton administration at that time had pulled out of ITER-1. ITER is that big thermonuclear experimental device that's now being built. It's sort of the biggest mega science project. It's a big fusion machine, and because it's tens of billions of dollars, no country alone is willing to foot the bill. So you have an odd club of participants who kind of can't stand each other in a way. I mean, you got Russia in there, and the Chinese and the Europeans and the Americans and Korea and the Japan and India and other industrialized nations. So you can think already the complexity of the political differences, the cultural differences, and now pulling tens of billions of dollars into a commonly built experiment. It's crazy, right? So ITER-1, the US pulled out. It got too expensive and too heavy, and I think that was a good decision. But with it, because it was a flagship sort of inspirational project for the fusion field, with it gone, the field was bit in, I don't say free fall, but total rework, right? And so whatever budget was left, if you came in as a newcomer now and say, I want part of the feeding trough, very difficult to envision. We tried for a couple of years, and that wasn't going to happen. And that drove us to think, is there a way to do this privately, right? And I think we were very, very lucky. We had a couple of really incredibly important people come into our orbit. Glenn Seaborg was one of those, who you may have read about, right? This discoverer of plutonium, won the Nobel Prize in chemistry for that work, and did a lot of work on basically atoms and nuclear physics and nuclear chemistry. Ran the Berkeley campus for a while, was an advisor to about 10 administrations through the rest of his life. a giant of science, a giant of science policy, really well connected. And he took a big liking to what we were working on. He thought the idea, again, end in mind, practical, seemed like a much better approach than the other stuff. Now, he wasn't a fusion physicist, but he deeply understood nuclear energy. And so that was helpful. And then around him, another group of really incredible but very diverse people that kind of all joined together, from Harry Hamlin, who is a environmentalist and actor, to people that built, for instance, like Alan Puckett, that built what became DirecTV. He was the CEO and chairman of Hughes Aircraft at that time. So it was a grouping of industrial people, finance experts, if you will, science and science policy giants, and it formed a nucleus around us that then allowed us to kind of take this crazy journey into private world of trying to develop fusion. We were the sole and only at that time, call it crazy enough, to go do and try. And again, the naivete was plentiful all across, but we all shared the passion and had this sort of quest in us that we wanted to make that happen. And so we launched it in 1998 as an entity and began in incremental steps building where we are today.
And the practical component of that is just so fantastically interesting. Of course, you have the theoretical, which some scientists and some nuclear fusion researchers devote their entire lives to and stay within. But I want to get into the practical side of nuclear fusion, because it really is a civilization-changing technology. Krish mentioned earlier Oppenheimer. The subtitle of that movie is The Modern Prometheus. Prometheus being the ancient Greek god who stole fire from the gods and gave it to humans. Now, on
price for it, I might add, right?
Exactly. And on the one hand, he was a favorite among the ancient Greek people. He occupied a very, very important place within their mythology as someone that really enabled human development. But on the other side, as you just mentioned, he was condemned for stealing fire and giving it to humans to suffer on a rock with crows essentially eating out his guts for the entirety of his life. Now, or for eternity, rather. Now, nuclear fusion to me, represents a new fire, essentially, a 21st century fire. And with that, of course, comes the enormous benefits associated with clean energy. You spoke earlier about a society, an affluent society with no real need that has solved this kind of resource problem. But on the other hand, if history tells us anything, it's that humans are not very responsible when it comes to new, significant, and drastic increases in power. What does a new, almost post-Promethean society look like with nuclear fusion once this practical component of the technology has been achieved?
Well, boy, that's a very deep philosophical question. I mean, the painting of a picture of the good side of it is straightforward, and I started it, but I'll go deeper because that's what motivates me. Your point about Prometheus, and of course his ending. First of all, I hope I'm not Prometheus. I'm not as great as that guy.
Yeah, I hope so too.
No, but I think there is a sort of you touched upon the darker side of humanity, right? And I will agree with that. I'm an eternal optimist, but I obviously see it. We all see it and experience it, and we're seeing it in other people. We find plenty of finger pointing we can do in ourselves, right, for that inherent human behavior. But if we can talk about that too a little bit, but let's talk about the positive stuff first, because I think that's sort of the center to me and why I do what I do. That's this notion of an age of abundance. And then, as I said, how do you transition to that? How do we cope with that? We can talk about it, because that's, I think, where the Achilles heel perhaps to it is. But if we start with the age of abundance, what does it mean? If you had a way to make power cheaply, with very few resources needed, in a very economic, practical, abundant way, you are enabling lots of stuff, right? So if you look at those fundamental things today, obviously healthcare, water, food production, the kind of minimal things we need to live, right? They all tie to energy, as I said earlier. And this would be enabled on a level we have not experienced yet. And so I think if you think of what are our next resource constraints? Well, energy is one, clearly. The environmental impact, although as I noted, and I don't want to get into the political debate around that topic. I stay away. I have really good friends in it, and I can tell you one of the things that actually motivated me was that when I was a graduate student, we had an experimental effort going during the days I was working on my theoretical PhD, which wasn't on our thing yet, but we were doing other plasma physics and accelerator work. And that lab was housed in an annex building, and it had above it a relatively small attic. And in that attic, UCI started a new Earth System Science department, which became part of the School of Physical Sciences and is today one of the shining stars. It's one of 4 departments. And it was a frontier place. There were very few at that time. And this was around the time just after Sherry Rowland had won a Nobel Prize, right, in chemistry for the discovery of the ozone hole and the mechanism behind it. Not the discovery of the ozone hole necessarily, but why that happens and how to fix it, the chlorofluorocarbon problems that linked to the Montreal protocols and cleaning that up, right? So his students and then others that nucleated around it formed the nucleus of this department, and they were starting to look at glacial ice melt and plankton in the ocean, and it really as a system study, not just looking at one component. And I think it still ranks not just as one of the best, but it's one of the few that is really integrated. And they were pioneer. So they were in the attic above us, and so I used to go lunch with these guys, right? And so I got this feed, which was not political at all, and they didn't study it for any other purpose, but they were curious, right? And we didn't understand. And even today, I'd say, knowing so many people in that field, I always get a little upset when people say, well, in so many years, we'll be 2 degrees hotter. I don't think you can quite say that. I mean, there are trend lines perhaps, but there's a very complex thing. And those people who are really deep in it don't know. But it was clear to us there is something happening. And that motivated me. I said, like, yeah, you know what? And it makes sense. I mean, why would you, if you have your own garden, you wouldn't put trash in it, right? Or keep it in your home, you keep it clean. Why would we dump? I mean, even forget for the moment if global warming happens or not, but just putting things out there that naturally aren't there, it will cause a change. May not all be negative, but it's a change. And so why taste that, right? It's beautiful out there and perfect. Why we mess with it? So those things were very clear to me. And I said to myself, this is important. So if you want to enable abundance, you have to do it not at the expense of something else that becomes constraining. And so when you look at this from this lens now, it doesn't have the constraints that potentially more combustion energy generation has. It doesn't have the resource constraints that we think may be there with oil and so on. It enables truly now an age of abundance that doesn't have those downside consequences to it. And again, the amount of boron, by what I said earlier, that we need to convert into energy is so little that it will not change the price of detergents. I can guarantee you that. The impact, in fact, we talked with the companies that make these products, and they were not interested in doing anything with us to say, like, look, you guys won't consume anything. I mean, compared to what we send over to the chemical companies, we're going to make any money with you guys.
Yeah.
And that's wonderful, right? So it tells you a story there. And it's that disinteresting from an economic perspective. Yeah, it truly is in a way free. And so you can think now the deeper jungles of Africa or rural India or parts of South America, those parts of the world today that are striving to get out of poverty, to get to a level of, I wouldn't even call it equality, because that's just probably not reachable near term, but a better quality of life, a fairer, egalitarian world where the gradients between the have and have-nots are much less steep. Fusion will give you that. I think it will. Now, to your point, that's the sinister part of humanity, right? Are we going to share it? Are we going to make it available quickly enough? And and if you look at the statistics, it tells you where the consumption is going to come from. I was quoting this earlier, right? Doubling of global demand. If you look at the increase in population, it's not that much. It's maybe 10, 20% or something. We're going to go from the 8+ billion to maybe 10 billion or so. But you will see a doubling of the consumption. That comes because, well, we will consume more too, but those guys will start to try, not pull equal yet, but get up. And so they're going to consume, right? And in fact, that's one of the things that always bothers me today when I think about that. Those of us who live in the West, we're beneficiaries of 150 years ago, the ignorance we had. We just burned from dung to everything, the steam engines and, whatever was available. And now we're telling others, no, you can't do that. Well, you know what? What right? I mean, I know in a way we all share the global sphere, but what right do we really have in the end, right? And they deserve to have a better quality of life. And I think this is one of the fundamental things that a fusion can solve. And I think that that's outside whether we ultimately combust too much and the planet goes, into a greenhouse gas meltdown. You don't need to invoke any of that. You just say fundamental equality of life elements. You can solve for that. You can solve for better healthcare. You can solve the water problems in parts of the world, because if you have cheap energy, we know how to desalinate. You can make it even better, probably with better technology, but you can filter and you press the salt water through it and you can get fresh water out of it. If you have enough cheap energy to do it, right? In abundant. Those are all things that start to become enabled. And so I think it's a very interesting concept. I was talking last summer at the Saudi Public Investment Fund derived thing they had in Miami, a conference, and invited me, and it was just a smaller group of people talking about this. And I was talking about the age of abundance coming out of fusion, and throwing out into the debate the question, how do we responsibly manage then if we have that? Let's assume we did. But first of all, what do we need to do to get there fast, right? Which we're not doing. The fact that TAE and a few other companies are spearheading that, and we have visionary investors beyond belief, who I can't believe are actually there. I'm so grateful, actually allow us to think about giving somebody $1 billion. We've invested in TAE about $1.25 billion so far over 25 years of now the company around. More than, it's going to be 26 years this April. Think about that, right? And of course, everybody thought we're going to be faster, to be clear, but people also never gave in. As I was saying earlier, once we came out of the fog, people still fulfilled their commitments and put more in, because they also saw a better chance now that we were closer to get there, right? That takes guts, incredible guts. I can't even imagine that, because I don't have money like that. And I know what little I have, I couldn't spend on that, right? But to find people that are willing to part with it for sort of an idealistic value set is incredible. And we're very lucky to have that. And so you put all this together, well, we need to do more, and we need more mobilization with global industrial sector, governments, policy, all of it, right? But let's assume we did that. And now we get to this age of abundance. How do we now really effectively share it and make sure this is available? Because here's the other side to it, right? In one way, fusion is wonderful because in the US, with our polarized political system, it has bipartisan appeal. If you believe in the environmental problems, you can argue, okay, fusion can solve those. If you believe or care about energy independence, national security, those kinds of things, you can find benefit there and say, like, yep, I don't have to worry about what happens in Saudi Arabia or somewhere else in the world. And think about it. I mean, how many of the recent escalations, I mean, there's sort of two drivers typically: energy or resource to energy, or religion, right? Like fusion won't solve religious problems, but it will solve the resource altercations, which are probably certainly the reason a country like the US or the West gets involved in. Typically, they always cover it and say it's democracy and religious freedoms and so on. But the reason is most of these wars are fought is because of resources. I mean, let's be real, right? And I think you take that away, a lot of what drives human behavior will have to adapt and adopt to this different paradigm. I remember I'm a European, right? So I was born in Salzburg, grew up in the south of Vienna, right next to the Iron Curtain. I used to go to a lake nearby there that was the border to Hungary, and they had it was a very shallow lake, shelf belt, and then, it's like not even 6 feet deep for most of it. You could walk across to Hungary, and people tried to do that. And so the Hungarians tried to flee that way. They put watchtowers up and machine gun turrets, and you see this, right? And so I was close to this stuff for a lot of my formative years, and thinking about, the impact of that, right? But if you look, when that curtain fell, the reset to our behavior was actually profound. It took a while to find new bearings. I mean, who are the new superpowers? Are there any? Of course, the US was there, but what is the new world order, right? Who is our enemy? Who are we fighting? I mean, I can tell you, for instance, Norman made this comment to me many times during the heyday of, the Reagan era, for instance, with Star Wars and stuff. Money was plentiful. There was a golden age of physics. And a lot of it, well, they got money to do basic stuff, but it was motivated by, let's find something that gives us a leg up on the Soviets and the evil empire, right? But when that was gone, that motivator goes away, and there's a lot less certainty about the flow of capital for fundamental science or the engineering adaptations of that. In fact, yes, when I came in, it was the end of that golden era of that free flow of the 90s, right? In a good way, because we didn't have that problem anymore. But that gives you an example of that I've thought about, of the kind of reset or rebalancing and finding new bearings and metrics to go on that'll happen. This is more fundamental, right? Because this affects abundance on the most fundamental way. It takes scarcity away. And as I said earlier, our economic principles, they all run on scarcity. What happens? I mean, if fusion, I mean, and it's not the cheap meter, to be clear, and I'm not saying that, but it can be so abundant that its economic impact will be felt dramatically across everything we do. How are we going to regulate value sets and therefore regulations, rules, laws, behavior? All of it will change, right? And that's going to be very interesting. And that part I can't tell you. I've philosophized about it with friends over social evenings and stuff. I don't know what will be the case. Of course, you can draw good and bad scenarios. I hope for the good in humanity will win. But I do know that it has the propensity to do a ton of good and to really fundamentally lift the underdeveloped part of the world into a better, standing. And I think that to me would be awesome.
This could be our moment for unification, I think, a sort of man on the moon mission again, for a lot of humanity. And I think it's so interesting that you mentioned the point on rural communities where if we can't provide them a sustainable alternative, how dare we tell them to get on the train with us, right?
Totally. See, that's my problem with this. That's a problem I have when I watch COP and those kinds of things. I mean, I'm all for cleaning the act up. Obviously, that's why I'm doing what I'm doing. But look at it, right? I mean, the reality is, who are we? And we, I mean, now the likes of us, Western people, have full half. The glass is beyond full. Tell those that don't know and by the way, it's in a way hypocritical, because we, on one hand, we say we want to help you. Yeah, you should have all of that. We feel bad that you don't. There are people protesting for that, but at the same time, they're saying, but you can't do it with the way we did it. You can't burn hydrocarbons. You can't burn your forests down and use your wood. But just to say that we did that, right? We did maybe not we, but our ancestors did it for 150, maybe more, to get to where we are. And it's the natural evolution, right? I mean, you learn from this incoming thing. So if we have a better solution, not only do we need to share it, we should concentrate deploying it there. Then it's not hypocrisy. Then you say, like, you know what, I'm going to help you lift yourself up. Not only do I want that to happen, but I'm going to give you the means to do it better than we did it. And you can actually leapfrog us in a way. That's the other interesting thing. That's another positive thing that I always love is, right? An example to that was, this was when I transitioned from Europe to the US. Cell phones weren't existent over there at that time, and over here, well, they were brick phones, right? But people had them, and then there came the next generation very quickly. Do the smaller handsets you can carry easily around, and you have to slug in your car, and with it came an early adoption of other things. Like, for instance, I remember you could start paying for parking on the 9 key. Over here that nobody had. Today, of course, it's everywhere. But there was a generational over turnover, where in a way the fact that there wasn't the legacy problem that you had to connect to allowed you to more freely leapfrog over that phase and actually get ahead in a way. So I could actually see that. It'd be really cool in a way, right? If you start a more modern grid, starting with a fusion power plant in the center, a much more efficient distribution system, more distributed energy in those developing parts, so they don't have to go and redo all the crappy stuff we did wrong or should have done differently in hindsight, right? That's what we should do. And are we going to do that? I don't know. That's going to be a question. And the good in me believes that's possible. Reality tends to unfortunately show us, right, that certain forces come in and they're going to want to exert control and in a way, with greed, extract the maximum juice, and that will likely lead to something probably different than optimal. But hopefully, at least in the end, it's certainly better than where we are. And I'm going to leave it there, because as it gets dangerous, and I don't want to be pessimistic.
No, let's talk about the timeline to put things into perspective for the listeners, but also for ourselves. I think Tay has a timeline that you recently, not recently, but have proposed, where right now we're at the Norman stage in the 2022. In the mid-decade, we expect Copernicus, which is net energy, and in the early 2030s, the Da Vinci prototype or the reactor where you can have net electrons. Could you explain to us perhaps, or I should first ask, is that still how it stands with how TAE has been progressing? Can we expect this in the early 2030s?
Yeah, I can certainly answer affirmative to the question of, is this still the plan of record? It is, absolutely. So Norman is still operational today. We run it every day, and we are transitioning, in a sense, all the engineering is on the new machine deeply. We are in construction. The facility that houses it, it's a brand new building that was erected for that purpose. That's done. We are beginning the first layers of, I wouldn't call it assembly yet, but the installation. There's a lot of guts work that goes on. You're putting trenches in for diagnostics and coolant channels and the kind of things. There's a lot of piping and plumbing and electrical and fiber optic that goes in first. And then you'll start to build the machine. So we think by 25, late 25, the machine will be in place. And I think within a year, and this may sound a bit tight, but we have a lot of experience running experiments now really efficiently. And we can talk about some of the machine learning tools we've developed and stuff that allow us to optimize faster any permutation of settings and knobs. So we're very confident we can, within a year, get to a state where we can validate that, yeah, this machine can make net energy.
That's fantastic.
And once you have that, then the race is on to go build a power plant. The Copernicus isn't yet. It's still a science experiment, right? I mean, it's going to measure, if you will. Part of this is synthetic, but part of it is exact measurements. But the synthetic part is very data calibrated, and so you have a high degree of confidence. You'll measure essentially the power coming from the grid versus how much power can you make in the core and how much comes out, right? And then you compare those two things, and then you also know that if you were to convert the power that comes out back to electrons to the grid, there's an inefficiency in a thermal system today that's about 50+%, a little more than 50. In the most modern systems, it's in the upper 40% efficient. So about 50+% is waste heat. And we will take that haircut. Then we'll say, okay, is that net left? Is that exceeding what we sucked out of the grid? And that's the goal. Once we have that, the race is on to go build a power plant, right? And yes, this is Da Vinci, and we think we can build that. I mean, we've been dreaming and more than dreaming, designing and redesigning and vetting different options for years. Both Copernicus, I mean, any one of those things. When you say now, what's the program, the project phase? By the time the project phase officially starts, like in this case, the building is there now. We're going to build the machine. So you can say we just started the Copernicus phase. The true Copernicus phase, in the sense, the planning, the thinking, started like 7-8 years ago. So it's there's an arc of effort that then culminates in the actual construction and reduction to hopefully the data sets that say, yep, milestone achieved. So Da Vinci, in a way, has started, again, almost the same time. I mean, we in parallel are kind of dreaming about the scientific minimum extraction of what we need to show the demonstration proof versus the full embellishment to go all the distance. And they diverge, of course, because in one case you have to have a lot more equipment on. You have a lot more long-lived operation in mind, right? The power plant's supposed to run ultimately steady state. Now, Da Vinci won't run like that. It's a prototype. It'll run, probably when we first turn it on, it'll run for minutes, and then we'll get it eventually to run for hours and maybe a few days. And it's never a perfect machine yet, but it'll get longer as it gets better at it. Anyhow, that there's an evolution there, right? And so Da Vinci is already being planned today, and we know we have a pretty good idea of what it will take in terms of componentry and some early costing ideas and all this kind of stuff. So I believe in this plan. I think it's completely realistic. It obviously presupposes that what we expect to get in Copernicus happens. If that doesn't, then we will not give up. To be clear, then we'll have to go back, and we're far enough that I don't think a catastrophic miss of the target data achievement is not going to happen on Copernicus. Da Vinci is too far out yet. I wouldn't. I would say we're confident, but I wouldn't make it that confident. That you have to. That's why Copernicus has to get done after all to give you that extra layer of confidence. But I think we're on Copernicus. We're very confident that we can. We operate, as I said earlier, say around 70 million degrees, 75 million. Some of the best shots, maybe some today are in the 60 to 70 million degrees. But we have a large data set in that vicinity. The Copernicus data point is 100 million plus up to maybe 150 million. So you're looking like a factor of 2 or so. This typically is not outrageous. I mean, if you look at any engineering extrapolation or scientific extrapolation, those are when you go to many factors of 10 or even factor of 10, then you're starting to say, okay, that's a bit of a stretch. This is really not. We have a lot of data. We have a lot of machine learning based systems that manipulate the machine and run it, that we have reduced to really incredible capability. All of that's going to get deployed again. So there's a high confidence on that. So assuming we succeed on that data point, then I believe a machine that gets to net electrons into the utility grid by the early 30s is absolutely feasible. And that's what we're trying to do. And I think we're not the only ones now, right? I mean, if you look, in fact, now you have a spectrum. I know Helion, for instance, is promising something this summer, net electrons. I have a bit of a hard time believing it's possible, but you know what? I wish them luck. And honestly, if they do, not only would I cheer for it, because it really doesn't change our economic, honestly. It's not, there's one winner and it takes the entire price and everybody else gets doomed. It doesn't work that way. First of all, until you have a real power plant, there's a lot more work to be done, number one. Number two, the market is enormous. I mean, you're talking next to healthcare, certainly the largest market on earth, right? Energy, that is. So it's not constrained to one company taking this market. Impossible. I mean, just like look at how many oil companies are massive companies, right? And they all coexist. Sometimes they compete a little bit, but not mutually exclusive in any way. So you have a vast infrastructure need for more power that's very well documented, and so there's a lot of space for lots of parties. And in fact, my biggest fear actually is that fusion will not have enough of a significant impact quickly enough. And so the utility of today, grid of today, is driven right by combustion-based systems that are burning hydrocarbons, by hydropower, nuclear fission, and then of course all the renewables that are coming on, which is great, right? So you have a lot of wind and solar, but that's variable power, so you have to figure out how to deal with that sometimes. The future grid over time will transition, and hopefully will use less of the combustion systems and more of renewables and fusion, and maybe fission as well. And eventually, late stage in the century, I would love to be at a point where fusion goes in as the base load for most things, and there'll be renewables in areas where they just make absolute sense because they're clean too and cheap and at that point and deployable. So I think it's that kind of evolution. So if you think about one takes the cake and timing pressures, yeah, we want to be fast, and I'd love for us to be first, but I think I could live being a happy second or third even. And so there's a couple of companies that are now in that time frame. I will say this, that I think what some of the more recent entrants underestimate, I mean, one is the technical complexity. Like I said, the journey is tough. And when you're not deep in it, you may promise something that you don't understand enough yet. You're not lying to anybody. I'm not suggesting anybody's lying. I think people are incredibly sincere. They're all incredibly motivated, but they are still naive. I was naive, and I'm still naive to a degree, but
You
I mean,
need that naivete.
You do, but you also, obviously you sober up, right? Because as you learn what works, what doesn't, and how hard it is, and the one thing I think that people underestimate next to the technical challenge is building teams to do it. And again, I don't know if this came out in the Oppenheimer movie or not, but Oppenheimer is one guy, and then it takes more than a village to do this, right? Sophisticated stuff. Like we have 330 people at the moment working on fusion, over 600 people in total at TAE as a family of stuff we do, and they don't work as individuals anymore. I mean, they're great individual scientists, but they've learned to work as a really formidable team. That is much harder to do than you may imagine. I don't know if what your backgrounds exactly are, but if you have ever been exposed to either physics or science in general or engineering, you will learn that there's a healthy rivalry between these two areas, right? the physicists or the scientists think the engineers are too superficial. They just take stuff out of a book or a table and then they run with it, and they never really understand fundamentally why it works. That's dangerous, right? At the same time, the engineers look down and say, these guys are way too in the weeds. They can never build shit, right? I mean, that's the kind of thing. And so, and that gets deeper sometimes. That gets to, or can I trust the other guy? Is he good enough to build what I need built if I'm the physicist? Or the other guy says, is this guy can even fundamentally tell me what I need to build him? We've gotten through that. And that was interesting, actually. When I first started building the team in the early 2000s, this was considerable energy spent. And it is a big, big risk factor. In fact, I would argue perhaps the biggest, even in something as complicated as making fusion work. Oh, yeah, because look, I mean, you can put a room full of Nobel laureates and say, solve this problem. The first thing that happens is, I mean, and I don't mean this in any kind of negative way, but they will have each a strong ego. They're very successful. They believe in their capability. And so the first fight will be, are they willing to listen to anybody else in that room, right? So you learn very quickly, if you want to build the right kind of team, you don't want only A+ people. You have to have a mix, number one. Then those that are A+ and alpha in character, they have to learn to come down from the high horse a little bit and interact better. And then at some point, people in science are groomed. Sometimes the pay is lousy at the university, right? But we live for the idealistic thing, the journey, the joy of discovery. But we also live, and I know this from myself and others, we live for some recognition. Maybe you publish a paper and then you'd love when people applaud to it, right? Or you win even a scientific prize. So recognition is a big deal. And so people are trained in a way to not share too much, because if you do, somebody else can run away with it and steal your recognition, right? It's sick. It is. And the university systems are very built on this. I could tell you a lot of stories about this. You want to get rid of that baggage, right? And you want to say, look, guys, this problem is so hard. We have to work as a team. And if we don't, there's no prayer in hell we can do anything. We're never going to succeed, right? And that's a big deal. And so the maturity of an organization doing it is very important as well. And I hope more than us have this, and I think some are getting there. And so I believe more than one will probably succeed, and that'd be wonderful.
And once you're able to create those really high functioning teams, the sky is the limit in terms of human ingenuity. Now we're close to running out of time. So I want to ask one more question before Krish asks a final one to conclude things. But all of this is just so tremendously exciting. The possibility, the fact that nuclear fusion represents a new kind of society, one significantly more affluent, more abundant than we've ever previously known, really does make it so that it's not a near zero-sum game. If someone gets to it, the world is changed. Now, I want to situate yourself quickly within this kind of revolution. You're someone that's been involved in this space, heavily involved, pioneering this space, in fact, for 25 years. And now with Copernicus being really a possibility within this decade, and Da Vinci coming afterwards, what are your personal emotions and feelings? I really only started looking into nuclear fusion in preparation for this podcast 3 or 4 weeks ago, and I'm imbued with this incredible excitement at the future and the possibilities of this development. How do you feel? I can't imagine my 4 weeks versus your 25 years.
I feel like the most privileged person on the planet to have been born into an era that actually can deliver that now, right? So I feel sorry, and I tell you at the same time, I feel profound sadness for Norman that he can witness this. And I hope he looks down from wherever he is and sees this, right? And just a story to bring this across. And, I can hopefully say it now without tearing up anymore. But this was about 2014. He was on his kind of deathbed. He was almost 90 years old, and he had onset of dementia and cognitive, issues. And there were good days and bad days. Sometimes he would recognize me, and some days couldn't. But his long-term memory was there, and he remembered fundamental things like what he did in his life, not nuanced, but the big picture stuff. And I came in. This was in November. He passed away Christmas Day of 2014. And this was in mid-November, later part of November. I can't remember exactly, but somewhere there. And I just came back from a conference, which was he always used to call it the meeting of the brotherhood. The American Physical Society Division of Plasma Physics does a meeting every November, early November, typically, where it's a general meeting. Everybody comes together, and because it's the largest physical society, and we're pretty much the largest fusion enterprise on the planet, from everywhere in the world they come in and for that meeting. It's a mega conference. And in 1998, Norman and I went to that same meeting in New Orleans, and this was right when we had started TAE, and they gave us, we had applied for to be able to give a talk. No, you don't give a talk. You can have I don't know if you know what a poster is, but you put up a framework of like a certain size of 4 by 8 feet or something on a board. You can put whatever you want there about what you're doing, graphics, text, equations, whatever it is. And then people walk by like in an exhibition, and they can interact with you and talk to you, but you don't, you get, it's very inefficient when you can talk to everybody. You just get the few people who care about that, perhaps. More importantly, so there's this big hall in this big convention center, and we get the last corner in the end. It was almost like a pointer's like, you guys are not even worth to be here. That's your point back there. Okay. And I was used to this already, because throughout my graduate years, we were kind of the stick that swam against the current in fusion. So, it's okay. We're there, and it wasn't very satisfactory, obviously. So now fast forward 2014, same conference, funny enough, totally by coincidence, in New Orleans, in the same vicinity, same convention facility, everything. Now, I was invited to come give an invited talk at this thing, and these are extremely hard to get. And we didn't even have to fight for it, because we'd made so much progress that people wanted to hear about it. And now, no longer in the back corner, I'm in an auditorium with hundreds of people listening. And when I walked out, it was the first talk of that session. Half the hall emptied and went in the hallway with me and wanted to learn more about it, right? And then we went out and published a paper out of it that became the most read paper of 2015 in our field by like a factor of 10. So that was the change in not acceptance yet, but in interest, right? And so I'm coming back from this high moment, and as I remember flying out of New Orleans, and the plane was taking off and circling on downtown going west, I thought of that moment, at that point, whatever it was, 16 years prior. And I said, man, Norman was sitting next to me that time, but now he's not, right? So my first thing was, I came back the next day, I visited him. He was in a home at that point, in a care facility. And, and I talked to him, and he didn't recognize me even. And I didn't care. I just told him the thing. And then he interrupted me, and we had it's common in our field that if somebody leaves the active phase, or they retire, or it's somebody that moves on, goes somewhere else, as a farewell gift, we give a picture of the machine that they've worked on. And then everybody in the team that's worked on it signs around it. And so those are kind of like, people have those on their walls in our field, right? And so if you've worked on different facilities, you probably have multiple of those. So he had one of those, and he was hanging in this room. His family put it up so he could see it across from his bed. And he pointed to it, and he said, do you know what that is? And I said, yeah, tell me about it, Norman. And he said, well, that's the company I started with my graduate student, and they're going to make energy abundant. And I got teared up. I still do a little bit.
It's so beautiful.
It's beautiful, but at the same time, he was just a knight. And 6 months earlier, I could have told him that, and he would have understood every vignette. And I said to him, I said, Norman, you're vindicated. The people that alienated you, that didn't believe you could do that, we could do this, and it was a shit idea, if you will, and for you, the corner, right? It was like, no, now there is an embracement. They don't necessarily all believe that this is going to happen, but they're interested. It's totally different. It's like 180 degrees, right? And by the cruelty of nature, somehow he was denied by 6 months to just leave here, knowing that, at least that I would have loved to see happen. So now coming to me, myself, I'm already fulfilled. I'm not looking for, I've had a fully blessed life. I mean, I've the full riches of doing what I love, working on one of the hardest problems perhaps. But I love doing that. I couldn't live without that challenge. I think it's morphed over the years. I used to do the deep science. Now I'm managing a big company, and I'm getting rusty on cranking equations. I can't do that as well as I used to when I was in my 20s. Obviously, in my mid 50s, I'm more using intuition now and relying on the team and giving ideas and stuff like that. And then they translate that. If you ask me to turn on the current machine, Norman, I wouldn't know where the button is. I mean, I'm kidding. I have a sense for it, but and that's just and it also tells you how many people you need to do this, and how appreciative I am to have this incredible team. And the other thing I think that happens as you get older, you become a little bit less edgy, less egotistical, maybe. For those of us who really have gone through hard moments, and I listened. I didn't read it. That's also on the shelf. The biography, the one on Elon. I haven't read yet. I did read the one on Jobs actually back then when it came out, and I recognized a bunch of parallels. I'm not Steve Jobs at all. I'm a completely different person, but there's certain things you realize when you go through evolving something like that and creating out of not nothing, but a lot of new stuff and motivating people to help you do that. It's interesting, and you live. I've always lived in this world where it already exists, in a way. And I saw this in the book. They called it there, or the people around Jobs called it reality distortion field. And I think it's actually a good term. I never thought of this. I wouldn't call it that. But there, and what's interesting is you have people that work with you who are there for the moment. They believe they contribute something meaningful, but they're happy with that. And if you were to ask a couple of those people, do you think we can ever build a fusion reactor? No. So why are you here? Well, I love the work and I love the challenge, and maybe and maybe it can happen. But if you ask me fundamentally, do I really believe it can? No, not necessarily. Now you ask me that, I say, oh hell yeah, we're going to make it, right? And I think I've always lived in a world where that already exists in a way. I knew it wasn't there, of course. I'm not crazy, but the idea was in my head so certain that then you can go to others and you can infuse them with enough optimism, I guess. And he's like, look, trust me on this one. You don't have to believe that we can actually build this, but here's what you have to do. If you do this and you carry that journey to here, and this person does that and that person does that, then trust me, then I can see it, that we can bring it together. And in the end, when we tie it all up, it will work, right? In a way, that's kind of been like it. And so, being allowed to get people to believe enough in that they want to listen to me, and or now not just me alone, but others on our executive leadership team to go do that, and then actually deliver these things incrementally, is just insane. It can be very lonely many times, and when it's hard, you go like, why did I get into this? And you have many more hard moments than the points of success. But boy, is it sweet when you get one. And that's kind of where I would leave it, saying the last thing to that question. In 2012 was the watershed moment where we went from the theoretical conjectures, if you will, coming out of the work I did with Norman during my PhD, to actually seeing it for the first time in the lab. This transition where the accelerator physics that I described a little bit earlier comes in and starts to change how this plasma behaves versus the conventional fusion plasma. We started to see that. And at that point, I knew we'd got it. I didn't know whether it was 10 years, 20 years, 30 years, where I would see it, but I knew this way was going to yield something really special, and you could see it. And the fundamental proof point was there, that the theoretical predictions we had were pretty darn well aligned with what we found in the lab. Okay. That was a high moment I can't even describe to you. The other high moments were building these machines, and when we first struggled to accrete $1, we built the first stuff we built. Norman and I took our credit cards and spent it up. I can tell you more about credit card debt than probably many people. It's crazy hard, and $10,000 was an insurmountable amount of money for us. $500 was a lot. And so we built these first things. The first thing we built was called a sewer pipe. It was this machine. We used a municipal sewer pipe part to make a vacuum system. And everybody knows a vacuum. You don't work with, fiber material and epoxy. Carbon fiber and epoxy is not your choice for that. Use steel and high quality materials that give you good vacuum properties. But that's all we could afford. So we started there. And then we started building the first machine. I can't even believe it's like 2006 or so. What became $100 million experiment. And I had to go out every night when construction started. I was the last guy out of the building, usually 10, 30, 11 at night. Dust had settled in the construction. I walked out and I made this was routine every night. You could see it if you watch the video of the security cameras, you would see me out there touching stuff. So seriously, as a pinch me, Michael, the stuff is real. We're actually resurrecting. We're freaking building this machine, and then that machine developed in 2012, this result. They're moments of fulfillment you can't describe, right? They're just, you live for those. This is like the adrenaline, I guess, when you climb Everest or something, that those people feel that can do that. I can't empathize exactly with it, but I think there's a similarity there. That is fulfillment to me. And, I would say I'm already so overflowing my bucket that if I get ultimately to deliver the final leg, well, can't even imagine, but I'm mentally prepared for it because we've dreamed of it for so long. It's incredible. And, I would say not only being privileged, but then to get the trust from all these people to allow you to do that at that scale, what more could you possibly ask for? And I don't care if I'm not into a prize or any of this stuff. It doesn't matter at all. It's just the idealistic value of delivering it is beyond fulfillment. I mean, that's it. you
I
know
think you mentioned Norman and some touching words and your feelings and everything that was going through your head. And I'm sure Norman is in the stars looking down and seeing so many great accomplishments, and then also beyond accomplishments, your vigor and your true sense of curiosity and awe, and how that's constant with such a truly noble task such as nuclear fusion. And it's metaphorical in some sense, because nuclear fusion is the replication of stars, such as what Norman I truly believe has become. I want to end on a note where I want to gather your hopes and thoughts for this next generation, this next civilization, if you will. One of the coolest ways of imagining the civilization I came across in research for this podcast was the Kardashev scale in 1964 that was put forth by Nikolai Kardashev, which was a progression of civilization in three types. The first type, he suggests, is planetary, which we're hoping to achieve through this nuclear fusion, where we control the planet's natural forces. It's 10 to the 16 watts for people who are listening. The second type is stellar, where this it's called the Dyson sphere, which was so interesting to me when I came across it, where you encompass a star and then take its energy, which is itself so magical. And the third type, which is 10 to the 36, or the galactic, where you control the energy so much so that you're moving between galaxies as a civilization. What is your next hope for this civilization that comes as a result of nuclear fusion, where we accomplish the task of planetary and we look forward, not from 0 to 1, but from 1 to 2? What's your next hope for the civilization, Michael?
Krish is about as cool a question as I've ever gotten from anybody. Okay. First of all, um, boy, I'm almost speechless how to answer that. I think, well, first of all, I think the taking small steps approach first, right? So I think that for me to have the nearest hope is this. We talk about this idea of this age of abundance, to not screw it up. Let's hope the next generation that gets these gifts, whether TA delivers it or somebody, but somebody will within the next 10, 15 years, will get that they can share that to the degree that it deserves and needs to be shared to truly reach the planetary stage you're describing. Because I think just having it as a concept and delivered into practice, now you got to go bring it out there. And to be clear, this is a big journey, right? I mean, as we said about how many, if you look how many power plants you would need, you're talking tens of thousands over a few decades. This is incredible scale. So you got to bring people together on every element, from the political side, the capital, the construction processes, the infrastructure behind the other upgrades that have to happen. I mean, it could go on, right? It's amazing. Let's make sure that happens, and that the generation that is going to steward this, which is, maybe you guys are young enough that you're probably going to be in the most active phase of your lives. I'll probably be retired. I hope I still be around to witness some of it. But that stage is going to be the one that's going to define whether this solution actually becomes manifest in a really impactful way. So that's the next stage. And I guess that's why I said this is the nearest step thing. Now you want to look further. I think it's clear to me what happens, right? Once you have that, you are now in possession of really looking beyond the ball we live on, no question. And I think if you think of practical space travel, one of the things that in my mind is missing today with chemical rockets is the time scales just don't work very well. I mean, you get to Mars for a human being, I mean, confined on a rocket for months, doesn't seem like a really good way of doing it, and one that would probably a lot of people would venture out on that journey. Maybe Elon is wild enough that he would actually do it. I don't know. Or a few very amazing discoverers that we have today too. I'm sure there's a modern Magellan or Columbus out there that's willing to go do that, right? But for practical purposes, you're going to need propulsion that's probably in a way that has the capability to shorten that journey for interstellar, I mean, or even stellar yet, but interplanetary travel. So I think fusion actually can provide a compact power source at the scale to do that. So that's a very big deal to me. Okay. And I believe that is a next journey. That's a next frontier, because you can't access the sort of exoplanetary sphere without that, right? And then I think once you master that, you can talk about colonization of Mars and those kinds of things, right? But it all starts with this, right? And so I think when you look at science fiction, there's a dividing line between the civilizations that have fusion, at least the writers portray it like that, and those that don't yet, right? And in fact, the next question is: are we truly the only ones out there? And are there others that already have fusion? May very well be the case, right? We never know, but we may also meet them one day.
It might
And
be a
maybe
fusion race.
tomorrow. Well, right? We don't know. It's a high degree of certainty that there's other intelligent life out there. I mean, there are infinitely, essentially, on the human scale, infinitely many possibilities of planets that have the right environment. Anyhow, my point is to you. So I think it's in these steps that I see it. I think let's make sure the planet is solid in its capabilities and its quality of life. Then you bring with it the ability to venture to the next sphere, which to me is a place like Mars. And then you have energy and other means to probably to the point of your energy scale. I totally agree. That's what you need to convert, for instance, to do terraforming there or something, right? To really evolve that to an environment you could live on. And then I think I don't know what comes next. I mean, God, that's amazing.
Well, I think, Michl, thank you so much for joining us today. I think the most interesting thing is you look at these particular technological developments, one that have moved us forth as human beings, as civilizations, the Gutenberg press, nuclear power, all these different things that have changed humankind's relationship to the cosmos. And this most definitely seems like the last one. Or the next one, the one in which we are on the precipice of jumping into. And while we will no doubt have no idea what that precipice looks like once we jump, it will nonetheless be a world like we can't imagine. So thank you so much for joining us today, telling us about your story, telling us about Norman's story, his legacy, the legacy of your company, and this fantastically interesting new technology. Thank you so much.
Thank you guys for having me. And honestly, the questions were absolutely invigorating and amazing. You guys did your homework. Kudos to that. That was absolutely awesome. I can't wait to see the output.
Nor can we.
It was incredible. I really appreciate it. And no, towards the end as well, I know when you talked about Norman, one of the experiences in my own life that I reflected on was my grandfather passed away a couple years ago. And he was a general surgeon in India, and that's what he did his entire life. And when we were on FaceTime with him, he was barely conscious, and he couldn't really remember us. And when he saw my sister, and my sister was born in India, and his hands were the one that delivered her. And when he saw my sister and he couldn't remember her, he said, "I delivered you." And it goes back to this sort of legacy, I think, that permeates through us. But beyond legacy, it's this conviction that is within our bones that I think you really embodied in the conversation today. And hopefully, I think more humans can do that. And I think nuclear fusion and nuclear power is one of the greatest steps humanity can take. And so glad to just get a glimpse into this journey that you're
guys, anytime. Thank
Absolutely.
you again. Look forward to it. Thank you.
Just so unbelievable. I mean, by far the most interesting podcast that we've ever done. And like Krish too, I kind of have a similar story as well. I'm named after my grandfather, so we share the same. He was born to an Austrian mother from Vienna. Yeah. And so he died 2 years before I was born, but I was named after him. And everything in my life, like everything that's been provided for, all my educational opportunities, everything are thanks to him. So although he's not around and he's never able to see it, it's just such a powerful thing to be having that kind of North Star.
Yeah.
That star literally kind of guiding
Totally
oneself.
forms you, right? In a way, it gives you grounding and it helps form you. I mean, and Norman, of course, because he was active in my life. For you, it's a grounding, your grandfather, right? For me, it was a formative person that was there during my probably most malleable and adaptable years, right? Where you're still elastic and can morph into something. And he helped shape that. And I mean, if I look at father figures, I mean, obviously my dad was a giant, and there's not one night that and he passed away about 10 years ago, unfortunately, too early. He was 73 at that time. But yeah, we all, unfortunately, this is the thing, right? I can talk about it now, but I lost him in 2013, and Norman passed away in 2014. So this is like tough stuff. And you look at that, and this kind of like, you don't get, most of us are lucky to have a wonderful parent, right? If we do, not everybody even does, but if we do, and I did, I had incredible home, both of my parents, amazing people. But then to get a second father figure, in a sense, right? It's just unbelievable. And Norman was that for sure. And then I got lucky with a few others who I wasn't as intense constantly around, like Arno Penzias and a few others, but also had benefits to learn there, right? This is one of the most beautiful things. And I think being able to cherish that and that lineage in the ways you described it, that you then carry on something, or you get infused with that knowledge and viewpoint, and you can make it your own and build upon it. It's really gorgeous, right? That's, in fact, in a way, part of what makes us human, right? And the evolution of technology, the evolution of knowledge, all of these things, in a way, we carry that DNA forward, right? That came back there. And some of us more intensely than others, but in a way, everybody does. And some do more consciously anyway, right? Than others. And so if you have the ability to consciously connect to it, which to me is it's fundamentally amazing thing, right? That can say like, yeah, you can actually see that. And I will tell you, it can also be a pressure in moments of, when we were building this thing and there were moments of desperation or kind of like bottlenecks, I thought of it and I said, man, the pressure is pretty high, because it's not just what I want, it's Norman's legacy too. Maybe it's Norman's legacy first, and what I want is second and almost irrelevant to it, right? You kind of, it is a good motivating force actually, but it's pressure. Yeah. Just like the investors who eventually would like to get paid back. Anyhow. Okay.
Yeah.
All right, guys. I really appreciate it. Thank you.
Yeah, thank you so much.
And when I come to California, I'd love to take a look.
Please do. Absolutely. If you guys are out in SoCal, come visit.
I'll actually be doing a research project along the West Coast this February. I know you're probably incredibly busy, but if you would have time for lunch, it's so fantastic.
I would love to if I'm here, and I'm traveling unfortunately a lot. It's fundraising forces that. But if I'm here, absolutely I do it myself. But if not, we have a really great team of people who can give a fantastic tour, eloquently explain it. Absolutely. Do just send a note, and you can send me a note, or you can send it to our PR team. Sure. They will absolutely, anyone will connect and make it happen anytime.
Excellent.
Just whenever you're in the area, come knock for sure.
Thank you so much, Michl.
All right.
Thank you. Wow.
I appreciate you.
I don't know what, we don't know what to say. Thank you.
Bye.
Take care. Bye-bye.
Thank you so much for listening to this episode of the Ivy Business Review podcast. To learn more about Michl, check out TAE Technologies, linked in the description. For other podcasts conducted with world-class leaders, check out the Leaders Corner on all streaming platforms.